So last time we looked at P and N type semiconductors, and we said that N type had an extra free electron and they existed in the conduction band, and P type had one fewer electron, so basically a hole that electrons can move into, and they exist in the valence band, and the electrons can move along into the holes in the valence band. In the N type, the electrons are free to move in the conduction band. So when we join these two together, this is the important thing, and this is how they work the best. So PN junctions are when we've got P-type and we've got N-type material together. Okay, so in a P-type material, we've got holes, and the N-type material, we've got extra electrons. You can see those little negatives there. Those are your spare electrons. Okay, now, as soon as you join these two together, the natural thing that happens is some of these electrons from the closest to here fill the holes here. So the electrons in the spare electrons in the N-type fill the holes in the P-type material. And so you get this area here, which is called the depletion zone, where those electrons have filled the holes, and nothing else can happen because they don't have enough energy for these electrons to skip over this layer to fill these holes. So what we call this a depletion layer, and it's very difficult to get past that depletion layer. So it's very difficult for electricity to flow. So for electricity to flow, we have to supply some energy for these electrons here to overcome this depletion layer and fill the holes here and have sort of a current flowing, so the electrons flowing. So we call this depletion layer a potential barrier because it's a barrier to any kind of current flowing. So to overcome that, we have to apply energy, and the energy that we can apply is a voltage, a potential difference. So you have to apply a certain amount of voltage for these electrons to then overcome that potential barrier, that depletion zone. And the voltage is usually about 0.7 volts. Now you've seen that value before with your transistors, and that's because transistors are made of, NPN transistor is made of PN junctions. So we need 0.7 volts in order for these electrons to overcome that potential barrier and carry on moving throughout the material. So to do that, we need to connect it the correct way round. So the way round that we want to connect it to is we want the negative part of the battery to be connected to, or the supply, to be connected to next to the N-type, so next to the electrons here. That's because we want those electrons to be repelled away from it. So we're giving them energy to go away from it. And we want the positive side of the supply to be next to the P-type. So these electrons are attracted towards the positive, so we want them to go in the direction that my mouse is moving. We want them to go that way. So they're repelled away from the negative and attracted towards the positive. So if that positive is and that negative is big enough, then those electrons will overcome that potential barrier, that depletion zone, and start filling in the holes over here. And it has to be enough voltage to do that, and it's usually around about 0.7 volts. If you connect it the wrong way around, so if instead you connect it with a negative there and a positive there, then that only serves to make this depletion zone even bigger because those electrons are pulled away. They're gone in the opposite direction. They're attracted towards the positive here. So if the PN junction is reverse biased, so the correct way around is called forward biased. The wrong way around is reverse biased. And basically it stops any electricity flowing. But the junction can only allow a tiny leakage current to flow because of the intrinsic semiconductors. Sometimes the electrons can become free just in a normal intrinsic semiconductor. But that's only a very, very tiny, tiny little part of a tiny current. So got a little diagram here of how we can talk about the bands in this. So I've just swapped around the P-type and the N-type here because it makes it a little bit easier to look at. So we've got P-type next to an N-type. So we've got P-type next to an N-type. So in a P-type conductor, we have got the holes in the bottom, and in the N-type, we've got the electrons in the top in the conduction band. So this is what it looks like here, p-type here, depletion zone here, and n-type here. We have some what we call diffusion, which is just the electrons next to the holes, just filling the holes next to them, which causes the depletion zone. That's your diffusion. So what we can see is if we don't apply any voltage to it, this we can see here that if we move the conduction band and the valence band upwards in the p-type, we get, and then we move the conduction band and the valence band downwards, so that Fermi level, that dotted line joins up, we get something that looks like this. So that's your valence band and your conduction band there for your p-type, and for your n-type, that's your conduction band and that's your valence band. And if we join those up together, we get these sort of a slanted line, and it produces what is kind of like a hill. Okay, and for those electrons to move into the p-type, then they have to overcome this hill. And if we apply a voltage, that hill can become smaller, so it's easier to overcome. Now, there's a few words here that you don't really need to know. Diffusion is just the natural electrons filling holes, which happens when we get the depletion zone. Drift is just the side that the electrons are normally at. So the filled in dot there is drift, that's the electrons on that side. The empty dot there is the holes, which are usually on that side. So basically what happens is this, when we put the two together, the conduction bands of the p-type moves upwards and the conduction band of the n-type moves downwards, and the valence band of the p-type moves upwards, valence band of the n-type moves downwards, and we get this kind of diagram here. Conduction band, valence band, conduction band, valence band, and the hill joining them up. And we've got a hill of energy to overcome, and if we apply voltage, that hill of energy can become smaller. And this is basically just saying the same thing as we said here, forward bias and reverse bias. Forward bias is when we've got a negative on this side next to the n-type and a positive next to the p-type, and that means that the electrons get repelled away from that negative and attracted towards a positive if it's a big enough voltage. Reverse bias is if we've got a positive here and a negative here, so the electrons, they get basically attracted the wrong way. We don't want them to go there because that just basically increases the depletion zone. It increases the barrier in the middle. We want them to overcome the barrier and therefore start moving. So reverse bias can only give you a tiny little current which just comes from the intrinsic semiconductor itself. Now there's an experiment that I'll show you which is basically showing you that you need a certain amount of voltage to then a diode to start working. So this is basically a diode setup in a circuit, and what we do is we measure the voltage across the diode and whether it begins to when it begins to conduct and when it doesn't begin to conduct, or when it doesn't conduct. So you find that when you do this experiment, you get a graph that looks like this. So it's basically the diode doesn't conduct until it gets to about 0.7 volts across it, and then it starts to conduct. Similarly, really, the opposite direction, it shouldn't conduct at all. But if you get to really high voltage in the opposite direction, you can get that leakage current, which is not really ideal, and it can damage the supply, the component. So the energy needed for current to flow to overcome the potential barrier is around about 0.7 volts. And I'll link you to that experiment just now.